Hey guys, Dia here, and welcome to a different kind of video where I show you something really cool. So here we have this line that is f of t equals t. F of t can be any function we want instead of t. It can be t squared, t cubed, or sine of t. Alright? So f of t is basically the function sine of t, where for some value like let's see here, like pi over 2 gives us 1. T equals pi makes f of t equals 0. That's all and good. But do you ever get bored of like the same horizontal axis, drawing the same wavy graph or whatever function it be? What if we can manipulate the x-axis to be something much cooler looking? So what I mean by that is, what if we can manipulate our axis as some sort of parameter controlled by these two functions, x of t and y of t? So if x of t equals t and y of t equals 0, it's basically just a horizontal line. So x of t and y of t, to remind you, is the axis that we would want to draw or attach this sine t of graph. So hey, if we can make the y of t sort of 0.01 t, our parameter is now a line that that increases as the x increases. So what I've done is, since it's the axis now instead of the horizontal axis, our sine graph also slants itself the further you go on this coordinate system. And okay, what if I make this line like 0.05 instead of 0.01? So here we have the sine wave that's even more rotated. And hey, what if our axis has different direction or rotation instead of just a straight line? What if we make y of t equal t squared, making our axis a parabola? So this sine wave now changes direction the further you go in. And as you can see here, the sine wave just swims along this new axis, and it gets even steeper the farther you go. And then we can make this t cubed. Same thing. So sine of t just swims along again to t cubed. Okay, what if we make our axis a shape of an ellipse? Instead of the sine wave diverging, instead we have our sine wave having this sort of revolution in an elliptic manner. And hey, you know what? If polar coordinates were still boring to you, now we have polar coordinates 2 electric boogaloo, where we have an ellipse instead of your regular circle. And I can make this sine t different. I can make this secant of t, and you will see chaos immediately. Now let me show you how I do that by showing you the equation that rules over this behavior. So here, let me zoom in. So here's the equation that governs everything that happened so far in this presentation. It's really overwhelming when you see it at first. You have this squared expression, this integral, and then you have this entire thing surrounded in f. So I will be explaining what this equation means, and I'll break it apart term by term and show you what each of these parts mean. But don't worry, nothing will be sort of hard when I explain it. And scripted me, I will pass this presentation to you. In this expression, we have 3 functions at play: xt, yt, and ft. Xt and yt together act as a curve representing the distorted x-axis of the result curve, while ft serves as the y-axis, which draws the result curve perpendicular to the distorted x-axis. These are the functions that create the curve itself, but how and why the curve distorts is defined by the expression's structure as a whole. So one way to better understand this expression is by thinking of these coordinates as vectors. By doing so, we could see that this expression is basically an addition of two vectors, where we add the first vector to this complicated second vector, which has this lengthy factor beside it, which we'll go through later. With that in mind, this first term here is simple. It simply is a vector of the parametric curve that will represent the distorted x-axis of the result curve. That's basically it. It's just a parameter. Now for the next term. Since this is the vector we add to the first one, we attach this to the arrow of the first one, where this vector draws another curve on top of the parametric curve. In our case, this vector draws the function ft curve relative to the parameter. By drawing something relative to the parameter, we can also say we are thinking of the direction perpendicular to the parameter. If x prime t, y prime t represents the vector parallel to the parameter, then by switching the components, then flipping one of them, would result in a direction 90 degrees from the parallel vector. Other than the vector's direction, one must also consider its magnitude. And this vector's magnitude is measured by drawing the arrow as a right triangle, separating its two components. To measure the arrow's magnitude, we utilize the Pythagorean theorem, where we acquire this square root expression. And hey, this squared expression here is the exact same thing as the denominator under the vector. So if the vector by itself has the magnitude of the square root, then dividing the vector by the same magnitude will reduce it to 1 unit. With the vector 1 unit long and 90 degrees relative to the parameter, we can draw whatever curve we want that rides along the parametric curve by manipulating the length of the vector through the function f. And hey, you know what? What if we just assign ft without the integral to control the magnitude? Well, it would look like this is the resulting curve that we wanted, but with one problem. The resulting curve is not evenly spaced out, and stretches as we go further off the parametric curve. And this is where the integral makes an entrance. The purpose of the integral is to fix the disarray of the stretching. You don't have to know what an integral is or why there's the similar squared expression inside it, but this guy right here represents the arc length or the perimeter of the parameter. Think of it like this. Imagine we have a horizontal axis and transforming it in some weird fashion where it maps itself into a shape. As the axis transforms, so do the ticks of the axis, yet still remain evenly spaced. This is what the axis would look like with the arc length integral, but without it, the tick marks would not be evenly spaced, where the ticks represent the values of t, which causes the stretch. This is why there is that integral inside the function f, to adjust those tick marks in accordance with the parameter's actual length to fix the stretching. To summarize, the expression is an addition of two vectors, where the first vector is a parameter that represents the distorted x-axis, and the second is a vector whose direction is normal to the curve and has a varying magnitude. This magnitude is first normalized to 1 by dividing by its Pythagorean magnitude. Then, a function f multiplies the unit magnitude so it draws the function normal to the parametric curve. And by having the arc length as the function's argument, the resulting curve prevents stretching and is drawn according to the parameter's relative units. And that's it for this video. I'm not gonna ask you to like or subscribe or anything. I just want you to enjoy or give you this sort of experience of graphs. And by experience, I'm gonna provide to you the link of this particular Desmos activity or calculator. You could use this, but I have a more organized link in the description. It's this one, offset curve 6, curve coordinates. This is the one that will appear in the description. When you enter, you will be encountered with the intro that has the Amogus wave in it, and the actual parameter that draws the actual crewmate You just have to like get the access of that crewmate thing, and then you have to increase the size by like tenfold, and then you do the sine wave. That's F of T. Like this one, like you zoom in or out, then boom. In the description, you'll find this link right here, and you know, you can tinker with the parameter or the function and get creative with it, you know. With that said, thanks for watching, and stay cool.